So, I hope you can see my screen now.
Perfect.
Yes, great. So I have a quite long title, but indeed I will cover all of that. Data models, classification models, and user interaction for pipe organs and pipe organ music. But first, I want to like to talk a bit about pipe organs. I do not want to offend you, but I assume you know nothing, and I give a very quick introduction. So there is an enormous diversity in pipe organs, from very small instruments like this with a cabinet size, which have, let's say, a quite intimate sound. For example, like this. Right? Uh, to big, majestic organs like this one in North German Baroque style, with which have a transparent sound, particular for music from the generation of Bach and before. Two instruments in French Romantic tradition, which have a more, let's say, woolly instrumental sound, for example, like this. Just to give you an idea. And if you follow this link, and the QR code is there, I compiled a while ago for a course, a playlist on YouTube with diversity of organ music. So if you want to hear more, have a look there. And this, of course, these three instruments are just the tip of the iceberg. And typically for pipe organs, each organ is unique. Each organ is tailored for a room. Only smaller instruments can be made in series, but even that there can be variation. So how does an organ work? Here's a nice cut through. So we have different components in an organ. Of course, you have the pipes. The pipes make the sound, right? Then we need wind. So every organ has bellows and a system with wind channels. And then, of course, we have the console. The organ must be played. So there are keyboards. And then there is the action, which is the mechanics that transfer the movements of the keys to the pipes. And last, there's the case, which is around the organ. And in this picture, you cannot really see the case, but because it's open, of course. But that's what, let's say, the box where the organ and the pipes and the action and the wind are in. So bellows can be very simple and very complex, but the idea is that the bellows make sure that there is a constant wind pressure that provides air for the pipes. And then the console. This is a typical console of an organ. So there are, in this case, there are three keyboards for the hands, three manuals. There's also a keyboard for the feet, the pedal, and you see a number of stop knobs, and I will talk about that later. The sound of the organ is generated by pipes, and basically there are two kinds of pipes. The one kind, which is here on the left, works like a recorder or a flute. So there's a labium that makes a fluctuating wind flow of wind, and typically sounds like this. And the other type at the right side has in the bottom of the pipe a reed, so a small strip of metal. And when wind blows in the pipe, the reed vibrates and makes a tone. And then the top of the pipe, so the cone amplifies that. It's not unlike an harmonica or a mouth organ or an accordion. They also, and a harmonium, they have also reeds, and typically sounds like this. And that is the tip of the iceberg. There's an enormous variety. By adjusting the shape, the diameter, the dimensions of all the parts of the pipe, it's possible to make a continuum of timbres, actually. And now to these stop knobs. With these stop knobs, the organist can choose which timbres, which kind of pipes to activate. And here's an example of that. Yeah, so if you would have a look inside of the organ, you see all those ranks of pipes. And basically, it's like a matrix. So each rank of pipes corresponds with one of those stop knobs. An entire rank can be activated or deactivated. And the other dimension corresponds to the keys. So each key is connected to one of each ranks of pipes. Yeah, and then there's the action, and this is just a video to give an idea of how that works. Right, so there's a system of wooden connections and switches that transfer the movement from the key to the pipe. Schematically, it's like this. So the pipes are wider than the keyboard, of course. So some kind of construction must be made to transfer the width of the keyboard to the width of the wind chest. That's where the pipes are on. And for that, there's this system with moving parts. Okay, I have one slide about history, just to give you an impression. This is one of the oldest organs in the Netherlands, and one of the oldest organs überhaupt. It's from the 15th century. This is 16th century organ, 17th century organ, we already saw. Typical 18th century organ, early 20th century, mid 20th century, 21st century. So again, huge diversity throughout the ages. So now I will talk about more about the projects that we did, the line of research we have at Utrecht University and before at the Medicine Institute in Amsterdam. It started with this series of books, with this we call the Organ Encyclopedia. The official title is Het Historische Orgel in Nederland, the historic organ in the Netherlands. And it's a documentation of virtually all organs of historic importance in the Netherlands, which are around 2000. And for each organ, the encyclopedia contains a history, technical specifications, running text with some peculiarities of the instrument, and literature references. And this was published between 1998 and 2010. So part of it is already old, so things have happened in between, and errors were discovered, and the book went out of print. So our aim in the Polyphonia project was to digitize all this information and to extract a knowledge graph from the full text of this encyclopedia. And with that, we had a musicological aim. So using all this knowledge, we can trace historical developments in organ building. And the NIVO, which is the National Institute for Organ Art, which is the publisher of the encyclopedia, they also have another aim. They want to make this data available in a public database. And so, yeah, for that reason, it needed to be digitized. Also, I do not want, again, I do not want to offend you, but I have a very basic explanation of what linked data is. So linked data consists of triples, and a triple consists of a subject, a predicate, and an object. In fact, it's a very simple sentence. And object in one triple can be a subject in the other triple, and then with that you can build a network. So for organs, this would be an example. Organ A, identifier of an organ. Organ A is an organ, right? Then organ A is in Concertbuilding Amsterdam. Organ A was built by Maarschalk Weert. Maarschalk Weert is an organ builder, etc. In this way, it's possible to connect all these triples together and build a network of knowledge. And particularly these is-a triples are important because they represent classes, right? This says that organ A is an instance or an individual of the class organ. And this network of classes in itself, that need to be designed. If you design a linked data structure, it's called an ontology. So this is the way we worked. We organized our workflow in actually in the entire project, the Polyphonia project. So we had interviews with potential users, and from that we extracted fictional persona, which represent types of users, and stories, which are the, let's say, the use cases or concrete versions of the use cases. And from those stories and persona, we extract competency questions, which are the questions that our system should be able to answer. And these, based on that, we construct interfaces for the users, and we use that for designing ontologies. And there's a feedback loop. We test it by examining whether our ontologies and our interfaces, our applications can indeed answer those questions, and ultimately whether the potential users are happy with it. And if not, then of course we can make changes. So that was the workflow. For the organ project, we had 3 personas. Amy was an organologist or musicologist and interested in music history. We had Paul, who is an organ advisor. An organ advisor is an official function, at least in the Netherlands. When an historic organ with a monumental status is being restored, then it's required that there is an organ advisor involved who oversees the project and makes sure that no historic material gets damaged or disappears, and thinks about what to do and what not to do. And then we had Frank. Frank is an organ enthusiast, and he, well, someone who just likes organ music. This is an example of a story. This is a story about Paul, the organ advisor. He's hired to plan the supervise of the restoration of an organ from the 16th century. Paul would look up the organ in the organ encyclopedia, which is ordered according to the year of production of the case of the organ. And here already we have something which is a difficulty in working with this organ encyclopedia, because if you publish a book on paper, then you can only choose one ordering of your of the items. And so a choice had to be made, and for the encyclopedia they made the choice to order the instruments according to the building year of the case. But sometimes a new organ is built in an existing case, but still then it's at the building year of the case, so it would not be at the place where you expect it in the encyclopedia, which can cause confusion. But well, again, I will not read all of this, but you get the idea. So it's a story about what Paul would do with the encyclopedia and what we would like to be able to provide an organ advisor with our applications. And from the story, we extracted a large number of competency questions, like all the things all the information we want to provide to the user. Which are all the organs in city X, which organs have stop Y, etc. We had in total like 60 or so. Then we had to design ontology. So this was the first sketch. And the nice thing of a big project like Polyphonia is that there's a collaboration with specialists. And I was not a specialist, still not. I'm not a specialist in ontology design. So the team in Bologna, where was the PI of the project, they took my sketch and they made this out of it, which has, I think, quite some clever ideas in it. So the idea is that an organ is represented as a parthood, and parthood, as the term tells, is something that consists of parts, and in this case, it is the organ case, right? The wind system, the console, the action, and the divisions, which contain the pipes. And the nice idea that for this particular ontology was that each of those parts has a time span and a location. And because of that, it is possible to track parts or pipes that move between organs. Sometimes, if an organ is deconstructed, parts of it are used in another organ. And so then you have the same part, but in another time span, it is at another location. And still that can be connected in a knowledge graph. So there are many more details here. I won't go into depth. But at the other hand, so we have projects. So there's organ itself, the physical object and everything, and there's everything that happens to it or with it. And all these are projects, like a concert that is being given, or a restoration, or a cleaning, or the organ is moved, or well, everything is a project, and that has a task, so a goal, and there are people involved. It can be an organ builder, organist, etc. And also projects have time and location. So then we had to take all the information of the encyclopedia, which we had in Word files, MS Word files. Those were the files that initially went to the printer. And with, it was an awful headache, but with quite some scripting and regular expressions and some clever prompts to parse all kinds of datings, etc. We were able to extract a structured version of this knowledge, and then with a couple of Sparkle queries, we were able to build this knowledge graph. This is just one example. So this object is a project, and the project has a task, which is restoration of a certain organ. I don't know which organ this is, but there's also someone involved, an organ builder with the name Ventrop, and it was in 1964, etc. So now we have this knowledge graph, and then apart from the organs from the Dutch encyclopedia, I added thousands of instruments from other online sources, open access sources, and in the end we have a knowledge graph of roughly 27,000 organs from Western Europe. And of course there's more. There are archives full of information that still can be added to this knowledge graph. For example, notations of organ specifications. There's a collection made by Jan Bouwman, who collected in his cahiers all the many specifications, but these are in handwriting, and We still have to find a way to digitize those. But anyway, then we have the knowledge graph. And then there's a Sparkle endpoint, and the user can type a Sparkle query to answer these questions, right? But the problem here is that of course, we cannot provide musicologists or organ advisors or organists with this. It's you have to learn to construct Sparkle queries, which is there are quite some pitfalls there. It's not very straightforward, I have to say. So we experimented a bit with interfaces. The first thing we tried was this kind of visualization in which each node in the knowledge graph is represented as a circle here, a node. And then you start with one, and by clicking on the relations, you can open the related nodes. Like this is an organ in Ulft, which is a city in the Netherlands. It was something to this organ was done in 1959 by a firma Pannenkoek and Vermeulen. And in 1959, some other things were being done. For example, there was done some work to the Marcus organ in Lauwenskerk in Rotterdam, etc. So by using this, you can navigate or find a path through the network. But yeah, you have to find a starting point, and then if a node has many relations like this 1959, you cannot see. It's difficult to browse because you cannot see it beforehand where all these connections lead. So you have to explore, and then your screen gets cluttered. So that in the end, that this didn't really work. So we experimented with another kind of interface. And this is mainly the work by Paul Mulholland at Open University in Milton Keynes in the UK, and also Jason Carvalho and Enrico Daga. Which the idea of this interaction is to provide the user with a more advanced way to find a path through the knowledge graph, and to build a path. And these paths, this contains stages, what we call a stage. So it's a connection of stages, and each stage can contain an organ, one or more organs, contextual information. For example, a YouTube video can be included. There can be text included, of course, interaction with the users. Maybe the best way to explore this is to show it. So this is an example of a path. So each path gets a unique URL, and these URLs can be shared. So if someone creates a path, for example, if an organ advisor creates a path through the knowledge graph for a certain project, it can share the path with a colleague and then ask for feedback. But here, so this is a path, I think, about organs in Alkmaar. And this is the first one with some text. And if there is a build history or a history of the organ in the knowledge graph, it's included like this as a table with the year and then what happened in that year, foldable. And if there are disposition included, and disposition is the specification of the timbres, the stop knobs that are present on the organ, then it's included like this. And if there are multiple, you can put them side by side, which actually is the first thing that the organ advisors all wanted in the interviews we did with them. They want to compare dispositions of the organs. So here, apparently, we have three. There's one from 1774, and then if we take one from 1885, you can see what changes were made over time. Apparently, some stops got renamed. The roerfluit, right? Octavefluit, cornet was added. Well, and then if you want to even compare more, there's here a link to copy this table, and then if you paste it into a spreadsheet like Excel, you can put more and then do everything you want. So that's for the dispositions, and then we go to the next stage. we would like, do you have some information? So this is a stage with where the user can, or the visitor of the path can provide some response, etc. Another organ, another organ. And so to build a path, there are so if you want to build a path, there are some search possibilities for to search in the knowledge graph. For example, if location. So I have made a collection of organs for myself, the ones that I want to use. I can search for location, all the organs in Vlaardingen, which is one, etc. And so each user can build his or her own collection to construct paths with. Okay, so then, and these can be shared. This is the homepage. So there on the homepage of this application, there are some featured paths, and you can search in paths, search for authors, etc. So go back to my presentation. This we have seen, this we have seen. Yeah. And so we provided organ advisors, the professional users with this, and they were quite happy with it, especially for crowdsourcing errors, because it is considered valuable to be 100% correct. So let's say with our, I mean information retrieval or computer science or AI, in our view, if we have 96% correct or 80% correct, it's already interesting, but these historians, they really want 100% correct. So one of the first things they said was, we can use this to get responses about maybe improvements or omissions or user feedback about that. The tabular representation of the dispositions they found interesting, and the possibility to share these paths with other users. Well, there's future work to be done here, and that and not go deep into it. Let's see, have a look at the clock. Yeah. So the idea of this path building and curating in itself is interesting, not only for organs, but also maybe for other heritage objects. And I know at Open University, they are working on this. So they are exploring this concept and how to employ it. Okay, that is about the metadata. And then for the second part of this presentation, I want to highlight some classification tasks we did as a continuation actually, of the Polyphonia project in the last 2-3 years. And I want to focus on 3 classification tasks with an audio track, so an audio recording of organ sound. We examined whether it's possible to recognize the timbre, so which stop knobs have been activated, to recognize organ type, for example, whether it is a Baroque organ or 19th century organ, and even that's very ambitious, to recognize the individual organ. So based on a recording, can we recognize which exact organ this is? We did this in collaboration with Organ Rocks, and Organ Rocks is a streaming service for organ music. So if you want to listen to organ music all day, have a subscription with them. And for us, it's interesting because they have the largest organ CD collection in the world, which consists of around 10, I think now it's 10,000 albums and about 150,000 tracks. Well, of course, if you compare this to Spotify, it's nothing. But if you compare, but for organ music, it's all there is, right? They assembled basically everything that has been published and as on CD. Actually, there's much more, especially on YouTube. There are thousands and thousands of organ recordings, but albums that have been released, it's around this 10,000. And they have all that, and also a database with high quality metadata. So for each track, we have of course, the album, but also the organist that's playing the track, the organ, and the organ is also connected to the history of the organ and the builder of the organ and the location, etc. So we have very rich metadata, which enables to train and test models on that. For all these classification tasks, we used a audio foundation model, Viola, which was published by Nizumi and colleagues in a few years ago. And they trained this model on the Google audio set, which is a set of around 2 million audio clips of each 10 seconds with 527 classes. And I looked into this audio set to see whether there's organ music in it, and actually there's not. There is organ, but it's most of it is electronic organ and Hammond organ, which is different kind of sound. So it's the data set that this model was trained on is basically unrelated to pipe organ sounds, but it is able to compute embeddings. So if you have an audio track, it computes an embedding in 2048 dimensional space. And we use those embeddings as input for a very simple multi-layer perceptron, just 3 layers, which does the classification. So for the registration recognition, which is the timbres, we used music from the French Baroque period, because that is the only period in which you can see from the title of the piece what the timbre should be. So the ground truth is in the title. For example, here there's concert de flûte. You know, there's flute. But this is already tricky. It says concert de flûte ou pont d'orgue. So it can also be pont d'orgue, which is foundational stops. But here there is basse de cornhorn, which says there is the cornhorn sound in the bass. Et dessus de cornet, the cornet sound in the right hand, in the upper part. Pour la voix humaine, that's for the voix humaine. These are all names of timbres. So by using the titles of these pieces, we have ground truth labels, and we extracted all the tracks from the collection of organ rocks with these titles. In the end, we had around 2,000 or so. And then this is a visualization, a T-SNE embedding, a two-dimensional embedding of the embedding vectors from the Viola model. So before our classification, and here you can see that already here the classes that cluster quite well, and in explainable way as well. For example, grand chœur and grand jeu is basically one cluster, and the sounds are indeed very similar, but still you can see they're separable. Same for basse de trompette, basse de cornhorn, which are very similar but still somewhat separable. So yeah, this works. So for to classify an entire track according to its registration, we get very high performing classification, sometimes even 100%. But the next thing we tried was to instead of use full tracks, to use time slices. In this case, we had time slices of 5 seconds, because in the course of a track, the registration, the timbre can change. So if you want to track these changes, you need to go to a lower time scale. And then the model breaks down, partly because we do not have ground truth for that. So we used the model that was trained on full tracks, and we classified all these 5-second time slices. And this is an example of some classifications. The classes are here at the left. And this is one track from a CD which has 6 movements, each with a different timbre. So the first is a grand jeu, sounds like this. So one slice is classified as grand chœur, and then there's some are grand jeu and some are basse trompette, which makes sense because the trumpet has also this reedy sound. The next movement is von Dork, which means foundation stops. It sounds like this. And here we see that some time slices are classified as duo, and some as basse de Cromorne. There is no Cromorne here, so that's obviously wrong. Duo makes some sense because, as you heard, there are two voices, but the typical timbre of the French duo is not here. So this is a real duo. So that's a more richer sound. There's a third in it, which is absent here. And yeah, just one more, the voix. So this is a movement for the voix. Sounds like this. Almost entirely classified as basse de Cromorne. And this is a real basse de Cromorne. So there's some similarity, but it's not, so this is not perfect. So we saw that on track level, this we had very good performance, but on smaller time frames, slices, it drops. And there's now a master student is starting to find ways to improve this and to try to understand why it fails. Okay, I very quickly go over the other two tasks. This is organ types. So we an organ expert from Organ Rocks provided labels for 139 organs: Renaissance, Baroque, Romantic, Symphonic. And here, based on the sound, we also get quite good classification results. And the confusion is understandable. So there's confusion between Romantic and Symphonic, and between Baroque and Renaissance, which indeed are related. So last task is recognizing an individual organ. And to show why this is challenging, I have two audio snippets from the same organ. So the model has to learn for the different timbres, which can be really different indeed, to recognize a particular instrument. And in this case, this was the organ in Bolbec in France. So we took two older organs with more than 100 tracks in the database, which are 239. In total, 56,000 tracks. And then, so we have a 239 class problem. And it appears that here that the tracks from the same organ cluster, we get quite good. These are the best performing organs. And most of those are quite famous organs indeed, with many recordings. And these are the worst performing, but still here we have, let's say, a respectable classification result. And also this should be continued to understand and to understand what makes the sound of the organs different. Okay, so actually, I have to say the work for this has been done in the viola model, because this model captures apparently the different characteristics of these timbres in such a way that it projects it in sensible regions in the embedding space. But we want to understand, why does the intra-track registration classification, so with the snippets, why does it fail, and can we improve it? So how to do it properly. And another next step is more fine-grained organ types. So not only Baroque, Renaissance, but German Baroque, French Baroque, Spanish Baroque, etc. And yeah, why does the recognition of the individual organs work so well? That's also a question I want to look in. And with that, I want to end my talk. Thank you for listening, and well, I'm open to questions and interaction. Thank you.